Neutrinos, the ghosts of the universe. Why, after millions of years of steadily lighting the cold darkness, does a supergiant star suddenly explode in a blinding blaze of glory brighter than 100 billion stars? What exotic objects in deep space are firing out particles at by far the highest energies in the universe? And perhaps the most mind-bending, why does the universe contain any matter at all? These mysteries have vexed astrophysicists and particle physicists for decades. The key for solving all three deep conundrum is itself one of the greatest enigmas of physics, the neutrino. So in today's video, we'll be talking about the all-time traveling ghost particles, the neutrino, and how it could answer some of the deepest questions in the cosmos, including why we're all here. Stay tuned till the end to find out. We are awash in neutrinos. They are among the lightest of the 24 or so known subatomic particles, and they come from all directions. From the Big Bang that began the universe, from exploding stars, and most of all from the sun. They go straight through the Earth at nearly the speed of light, all the time, day and night, in enormous numbers. About 100 trillion neutrinos pass through our bodies every second. The problem our physicists is that neutrinos are impossible to see and difficult to detect. Any instrument designed to do so may feel solid to the touch, but to neutrinos, even stainless steel is mostly empty space, as wide open as the solar system is to a comet. What's more, neutrinos, unlike most subatomic particles, have no electric charge. They are neutral, hence the name. So scientists can use electric or magnetic forces to capture them. That's why physicists call them ghost particles. Beyond expanding the role of neutrinos in astronomy and uncovering their role in astrophysics, physicists are still trying to discover some of the neutrinos' basic properties. Some researchers, for instance, are trying to pin down the particles' possible masses. That fundamental information would influence theories that explain the masses of other particles. By determining yet another elusive fundamental properties of neutrinos, researchers also hope to answer one of the theoretical physics' great riddle: why all the matter and antimatter created by the Big Bang didn't cancel each other out and leave nothing but energy. At the dawn of the universe, for every particle of matter, such as an electron, there was an anti-electron. For every quark, there was an anti-quark. When these opposites meet, they should annihilate each other, creating pure energy. If that's the case, then why is there any matter left? The most plausible solution hinges on the theory that today's neutrinos, which have barely any mass, once had super heavy partners. These neutrino cousins, 100 trillion times more massive than a proton, formed in a tremendous heat and existed right after the Big Bang. For this theory to explain why matter exists, those early super-heavy neutrinos would have had to decay more frequently into particles than antiparticles. If the super-heavy neutrino theory is correct, then these primordial particles are the supreme ancestor from which every particle in the cosmos descended. Scientists who want to detect neutrinos must build their detectors deep underground or underwater to filter out the cosmic rays that constantly bombard Earth. Francis Hausen, a physicist at the University of Wisconsin-Madison, realized decades ago that Antarctica was an ideal spot because the ice was thick enough to bury thousands of light sensors more than a mile deep. When a neutrino chances to slam into an atomic nucleus in the ice, an electron or muon, a heavier cousin of the electron, is created, releasing a trace of light. That trace of light can be picked up by IceCube, an underground telescope detector at the South Pole. In May 2012, IceCube physicists discovered the light footprints of two neutrinos with an incredible 1,000 times more energy than any neutrino ever detected before on Earth. These neutrinos almost certainly hail from beyond our galaxy, and they could help solve a century-old mystery about the source of incredibly high-energy cosmic rays. That source is also thought to produce high-energy neutrinos. Some possible scenarios: incredibly massive black holes erupting in jets of matter, galaxies colliding, or star-producing factories known as starburst galaxies. So, where do neutrinos come from and why they are so cool? A star implodes in a cataclysmic burst of energy. A scientist measures the small energy discrepancies of radioactive decay. The sun constantly bathes us with warmth and showers us with particles. All around us, the universe is saturated with the remnants of the Big Bang, and in all of these things, there is one thing in common: neutrinos. Although they are hard to detect, these little particles can tell us about everything from the birth of the universe to the nuclear reactions that power our cities. On February 23, 1987, detectors deep underground that were designed to detect proton decay suddenly detected a huge number of neutrinos. Scientists were perplexed by this influx of neutrinos from a supernova in the Large Magellanic Cloud. This was a core collapse supernova. When the core of a massive star collapses, it crushes the protons and electrons together and neutrinos form. The neutrinos pass straight through the collapsing star before the explosion takes place. This is why the neutrinos were detected before the supernova was visibly observed. When the neutrinos leave, they also take the energy away from the star, and the star continues to collapse and rebounds in an explosion that can outshine the brightness of the entire galaxy. Neutrinos are very important to the study of supernovas because they provide an early warning signal and allow scientists to be looking in the right directions before the supernova even takes place. Neutrinos are also created in the nuclear reactions that power the core of stars like our sun. Neutrinos are formed in the proton chain. Neutrinos are important because they allow scientists to peek into the interior of the sun and learn about the process there. All other information about the sun is from electromagnetic radiations that has to pass through the many layers of the sun, interacting and changing along the way before traveling through space to us. This whole process can take a million years. However, the neutrinos pass cleanly through the sun in a few seconds without interacting and take a mere 8 minutes to travel from the core where they are created to us. Since we know that extreme cosmic objects and events can produce neutrinos, for instance, exploding stars or supernovas are known to create neutrinos and shoot them across the universe. So are supermassive black holes chomping on gas, dust, and stars. So, by detecting neutrinos, we can unveil the mysteries behind these cosmic objects. Because they hardly interact with the surrounding matter, we could use neutrinos to see these types of objects and understand them in regions of the universe we can study with other electromagnetic wavelengths. For example, scientists could peer into the heart of the Milky Way, which is hard to observe in other electromagnetic wavelengths because our sight is interfered with by gas and dust. Reliable detections and tracing could stimulate an astronomical revolutions akin to the one we are currently seeing with gravitational waves. Essentially, neutrinos can give us a whole new eye on the cosmos, complementing our existing set of telescopes and detectors to reveal what's going on in the void. So, what are the mysteries behind the recently detected ghosts of the universe? Neutrinos are referred to as ghostly because they are extremely vaporous particles that can pass through any kind of matter without changing. They have almost no mass. They can travel through the most extreme environments like stars, planets, and entire galaxies and remain the same. Before July 2018, only 2 sources had been found: the sun and a supernova. When the initial studies of the neutrino were released last year, astronomers said the galaxy where the neutrino originated had a supermassive, rapidly spinning black hole at its center known as a blazar. Now, the researchers think that there are possibly 2 supermassive black holes in the central region of this galaxy. The black holes act as an engine powering the galaxy, making it one of the most energetic objects in the universe. A blazar is a giant elliptical galaxy with 2 jets emitting light and particles moving close to the speed of light along with the axis of the black hole's rotation. They can flare for minutes or months. One of those blazingly bright jets, hence the name blazar, is pointing at the Earth. But there was an unexpected interactions of the jet material where new materials crash into older jet material. It's possible that the jets were curved, allowing these cosmic collisions to happen. Either way, it leads to a neutrino. Scientists have thought for some time that energetic particles could be created by these jets because they could act as cosmic accelerators, affecting protons and neutrons and turning them into cosmic rays. Because cosmic rays have energies up to 100 million times those of the particles in the Large Hadron Collider. Only something spectacularly violent could create them. Then, after interacting with another material in the jet, high-energy neutrinos could be created from those cosmic rays. Though we've been able to detect and trace only a few neutrinos so far, the next decade should see neutrino astronomy really take off. The bottom line is that understanding neutrinos, their flavors and masses will provide a window into the fundamental nature of our universe. And it's always cool to chase ghosts. So, what are your thoughts on this exciting new development? Do you think we can still unveil the mysteries of the cosmos by detecting the so-called ghosts of the universe, the neutrinos? Let us know in the comments below. That's all in this video. Thanks for watching. Be sure to like and subscribe to our channel and press the bell icon to get all the regular updates. And we'll see you in the next one.